Namaste, welcome to the lecture series on the subject Basic Thermodynamics, Module 3, Part 2, Entropy, Lecture number 17. Myself, Dr. Satheesh Kumar, Associate Professor of Mechanical Engineering, Canara Engineering College. So once again, with request from the students, I intend to solve two more numericals on entropy calculations in this lecture. Let us solve this problem. 1 kg of ice at minus 5 degrees C is exposed to the atmosphere, which is at 20 degrees C. The ice melts and comes into fine thermal equilibrium with the atmosphere. Determine the entropy increase of the universe. Universe means atmosphere replaced ice, you have to calculate. So 1 kg of ice is at minus 5 and it is exposed to the atmosphere, which is at 20. So what happens is, so ice at minus 5 melts and becomes water at 20. So here three stages of melting or conversion of ice to water. What is that? First, ice has to come to 0 degree Celsius from minus 5. So minus 5 to 0. First step, phase 1. Then ice at 0 to water at 0. Second phase, where latent heat comes into picture. Then third stage, where water at 0 should become water at 20, where the specific heat comes into picture. So let us solve this problem. So this is a diagram. So atmosphere is at 20 degrees Celsius and ice is at minus 5. So heat amount of by an amount of Q is transferred to ice to convert it into water at 20 degrees Celsius. Now here atmospheric temperature doesn't change because it is considered as the reservoir. That's very, very important. So here Q, whenever you calculate, so you have to calculate it as summation of three terms, that is heat required to increase the temperature of ice from minus 5 to 0, then melt ice at 0 to water at 0, then increase the temperature of water at 0 to water at 20. So I'll show it in the next slide. So heat absorbed by the ice from the atmosphere is given by, now this is the formula. You see, that is what I told. The Q term here is equal to, first is ice. You see, ice melting from minus 5 to 0. So ice minus 5 to 0, one phase, plus phase 2 is ice. You see, ice at 0 to water at 0 to water, okay, water at 0. So there where the latent heat comes into picture, plus next stage is water at 0. You see, it's not directly ice converting into water. So there are three steps involved. Water from 0, let's bracket, okay, 0 to 20. So this is very, very important. Everybody has to understand this. Okay. Now what ice from minus 5 to 0 means 1 kg, okay, that is mass m, specific heat of ice into 0 minus of minus 5, because final temperature is 0 minus initial temperature is minus 5, then plus 1 kg into latent heat of ice, just latent heat, where when ice at 0 to converting into water to 0, only latent heat comes into picture. So then water at 0 to water to 20, so specific heat of water comes into picture, which is 4.187, final temperature is 20, initial temperature is 0, so 20 minus 0. So 1 is common actually, mass, you can take it outside or you can multiply into each of these terms. Okay, so you'll get the answer Q as 427.5 kilojoules. Now this is the amount of heat given by the atmosphere or absorbed by the ice when its temperature changes from minus 5 to water at 20 degrees Celsius. Now entropy change of atmosphere, because atmosphere is giving this heat, so this quantity has to be minus Q for atmosphere, but its temperature is constant 20 because it is considered as a reservoir, so it is 293 Kelvin. So minus 427.5 by 293, so its entropy change becomes minus 1.46 kilojoules per Kelvin. Now entropy change of the system ice. Now it has to be calculated in 3 steps. First step is when it is heated from minus 5 to 0 degree Celsius. So it is 268, minus 5 is 268 to 273, or to integrate mCp dt by T. So if you substitute and if you simplify this, so you will get it as minus 0.0389 kilojoules per Kelvin. Now second step is the entropy change of the system, that is ice melting from 0 to and becoming water at 0, wherein only the latent heat comes into picture and temperature remains constant during this phase change. You see here temperature changes from minus 5 to 0. Look at here. But here ice is at 0, water is at 0, no temperature change, it is just latent heat by temperature, that is 273. So this will get it as 1.22 kilojoules per Kelvin. And the third phase, entropy change of water as it is heated from 0 to 20. Once again temperature change is there from 0, that is 273 to 293 here. So mCp dt by T out integrate, and after proper substitution and simplification you get it as 0.296 kilojoules per Kelvin. Okay. Now to find out the total entropy change of ice as it melts into water, so to add delta S1, delta S2, delta S3 to get the delta S total as 1.5594 kilojoules per Kelvin. Now the entropy change of the universe is nothing but entropy change of the system plus the entropy change of the atmosphere, so you'll get as 0.0949 kilojoules per Kelvin. Now we'll solve one more problem. A 5 kg copper block at a temperature of 200 degrees Celsius is dropped into an insulated tank containing 100 kg of oil at a temperature of 30 degrees C. Find the increase in entropy of the universe due to this process when copper block and the oil reach thermal equilibrium. Assume that the specific heats of copper and oil are respectively 0.4 kilojoules per kg per Kelvin and 2.1 kilojoules per kg per Kelvin. So 5 kg of copper and its temperature is 200. Is dipped into a tank containing oil of mass 100 kg, which is at a temperature of 30 degrees Celsius. I hope similar problems we solved earlier also. You have to find out the entropy change of the universe due to this process, wherein the specific heats of the copper as well as oil are given. So let us solve this problem. Okay, now let us solve this problem. So let us note down the given data in tabular form. So one column copper block, one column oil. So note down temperature of both the copper and oil, mass of copper, mass of oil, Cp copper block or C copper block, C oil, and let us take Tm as the intermediate temperature, because here copper loses its temperature or heat and its temperature decreases, where oil absorbs the heat lost by the copper or heat given by the copper and its temperature increases to Tm. So copper is giving its heat, so that is nothing but heat given by the copper is Mc into C copper into Tc minus Tm, where oil absorbs heat, so it is M oil C oil into Tm minus T0. Okay, this is Tm. So Tm, if you calculate, if you simplify the formula first, it becomes McC copper into Tc plus M oil C oil into To divided by McC copper block plus M oil C oil, and if you make proper substitution and simplification, you will get the answer as 31.6 degrees Celsius. Now here, suppose if you substitute in Kelvin, you will get Kelvin, otherwise you will get it in Celsius. Okay. Now if you calculate the entropy change of copper and oil, so copper, its temperature is decreasing from Tc to Tm, you can see here. So Mc C copper block into dt by T, usual formula, integration, all those things, you will get it as negative because it is losing its heat, minus 0.8802 kilojoules per Kelvin, whereas the oil, its temperature is increasing from initial temperatures To to equilibrium temperature Tm, similar formula, but it is for oil. Proper substitution and simplification, you will get as plus 1.106 kilojoules per Kelvin, plus because oil is absorbing the heat lost by the or heat given by the copper block. Now the entropy change of the universe or the total is nothing but the delta S copper block plus delta S oil, so which comes to 0.2258 kilojoules per Kelvin. Okay, so with this I conclude this additional lecture wherein I solved 2 more problems on entropy calculations. Okay, thank you.